Good evening, ladies and gentlemen. My name is Benny. I'm going to present to you the design for water supply infrastructure for 6 townships located within the Limpopo municipality. This is the schematic layout of the townships. As I said, there are 6 townships, 3 situated this side of the town, 3 on the other side. We have the existing river here. In between the existing river and the storage reservoir, we have a water treatment plant, and the reservoir is situated uphill. So the idea is that the pipe from the river to the water treatment plant and the storage tank will be water mains, meaning that water will be pumped up, but from the storage tank, it is gravity. What's required for this project is that we must get the correct sizes for the pipe. We must maintain the velocity within the pipes below 1.5 meters per second, as per the guidelines for human settlement and planning design, which is used in South Africa. And also another important parameter is to keep a constant head of 20 meters at the demand centers. Some of the information that's given to us is that the storage tank should be sized such in order to maintain 8 hours of supply without being pumped. And the pump caves should be set at 80 meter head with equivalent supply of 600 liters per second. And as I said earlier, very important to keep the velocities below 1.5 meters per second, and also the head losses in the pipes at 10% or below 10% from the available head. The 6 demand centers has got a total demand of 10,950 cubic meters, which must be maintained for 8 hours without being pumped. But a given size of the storage tank, which is 11 meter high by 35 meter diameter, is only equal to 10,583. That is less than what is required at all 6 demand centers. So that means the size of the reservoir is wrong. I have increased it from 11 meter high to 12 meter high. That gives me 11,545 cubic meters, which is sufficient. There are some empirical formula that were developed many years ago, which are used in design of water distribution systems. The reason is that, for example, the one that I'm choosing as an input in this software is called Hassem-Williams head loss formula. It's an equation for calculating head loss in pipes due to friction, relates flow of water in pipe with physical properties of the pipe. What it means is that depending on the type of material we use to make a pipe, if it is a concrete pipe, steel pipe, or a UPVC pipe, the water that flows inside the pipe rub against the inside wall of the pipe, so which we describe as a friction. So some pipes are smooth, some are rough. So that's where there is a certain empirical constant that was developed, which we called a roughness coefficient. So in this case, we're going to use a roughness coefficient of 100, and that is a criteria or an aspect which is incorporated within this Hassem-Williams head loss equation. Pump caves, as I mentioned earlier, set at 600 liters per second with a 80 meter head. Hydraulic infrastructure consists of, there is an obstruction at the existing river, 2 pumps. 1 pump will draw water from the obstruction, which is the river, and pump it to the water treatment plant. Second pump will pump water from an outlet which is 5 meters below the water treatment plant into the storage tank. Since the storage tank is situated high on top of a hill, water will flow by gravity through up until it reaches the demand centers. So water will not be pumped from the storage tank. Pipes were sized initially at 300 millimeter diameter. Test run was carried out. It came out unsuccessful. This is due to negative pressure that was obtained at the end, at end nodes, the demand center, meaning that the sizes of the pipes are inadequate. So we need to do about the pipe sizes. Then the diameters were increased. For example, for demand center 1, which is pipe 6 to 350, 350 and 350 millimeters diameters there. Pipe 4 was set at 500, pipe 5 at 600, and so on and so on. And the pumping mains also increased up to 1,000 millimeter diameter and pipe 2 up to 800 millimeter diameter. When the test run was carried out, this time around, we got sufficient head at each demand center. Looking at a given legend here, that yellow color indicates that the head lies between 75 and 100 meters. So you can see that each node here is yellow, 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 meaning there is a constant head has been achieved or maintained. Likewise, the losses within the pipes, the links, pipe 11, pipe 6, pipe 7, is also kept below 10%. As indicated here, 0.79, that is the loss in that pipe head loss compared with the available head from that section. So having a look at this table, available heads and the 10% of the available head are these red figures, but the losses in the pipes 3.9.1, 1%, 0.5 is way below 10%. So that is also a good indication that the design is good. The software is also capable of providing us with the information such as, for example, the velocity below 1.5 meters, and it kicks out all these links are red, meaning the velocity, flow velocity within each and every pipe is below 1.5 meter, which is okay, per second here. And also same for the demand centers. Give me the pressure above 20. That's the query, that's the input. And then it gives you the centers, which has a pressure head of above 20 meters. So we achieve constant pressure head. We achieve velocities below 1.5 meters per second. We achieve the right sizes of the pipes. And there is no negative pressure experienced at the end node. So the design is successful. So for this reason, the municipality may go ahead and install the water supply infrastructure. Thank you.